Okay, so last year's paper, 2024, question 35, 7 marker. Unknown samples of three carboxylic acids labeled X, Y, and Z are analyzed to determine their identities. Both Y and Z react rapidly with bromine in the absence of UV light. Do you get anything out of that? Y and Z can react rapidly with bromine when there's no UV light. That's a brown bromine water test. Yes, to distinguish between alkenes and alkanes. Good. Alkanes can react with you can react with alkanes can react with halogens, bromine, if you've got UV light. Yeah, which means if you don't have UV light, it shouldn't react. However, Y and Z, even though there's no UV light, it still reacts, which means it's not an alkane, it must be an alkene. Good. If you want to react alkanes with halogens, in this case it happens to be bromine, you need UV light to do that. But it doesn't have UV light and it still reacts. That means they're alkenes. What's the functional group for an alkene? Carbon-carbon double bond. Good. Okay. But X does not. So both Y and Z react rapidly with bromine in the absence of UV light, but X doesn't. So Y and Z do, they're alkenes. If X doesn't, after what we've talked about, X must be what? Y and Z are the alkenes, X must be the alkane. With what kind of functional group? Carbon-carbon single bond. Okay, cool. Let's see if you can start figuring out the structures yet. Yeah, so we're gonna evaluate as we go, see if we can start figuring anything out straight away so that I don't have so much information to combine together at the end. These are your three possible structures. Okay? Let's see if you can start figuring anything out yet. So Y and Z are the alkenes with a carbon-carbon double bond. So Y and Z, that's two letters, which means it has to be two of these structures, yeah? Which of these structures, one, two, or three, have the double bond that you're looking for? One and three. Good. So one has a double one here, and then three has a double one right in the middle. So we don't know yet which one's Y and which one's Z, but we know of them, Y and Z are structures one and three. Which means, guys, by the process of elimination, compound X, which has carbon-carbon single bonds, has to be structure number two. All right, so at least we figured out one of them, okay? X is structure two. A 0.100 gram sample of Y reacts with the same amount of bromine as a 0.2 gram sample of Z. So we'll have to do some kind of mole calculations, which depends on what Y is and depends on what Z is, but I haven't figured out the structures yet. Separate 0.1 gram samples of X, Y, and Z are titrated with 0.0617 mole per liter sodium hydroxide. The tidal volumes are shown. 21.88, 22.949, and 22.49. Third dot point, both Y and Z can undergo hydration reactions in the presence of a suitable catalyst. That aligns with what we've said. If you want to do a hydration reaction, you need to have a double bond. We've already said that Y and Z have a double bond. So this third syllabus dot point gives us the same information or helps us come to the same conclusion that the first dot point did. That's fine. Hydration reaction in the presence of a suitable catalyst. What is that suitable catalyst? Just to revise as we're going. Dilute H2SO4. Good. Which is because it's a hydrating agent. Two products are possible for the hydration of Y, but only one product is possible with Z. Now hold on. We usually get two products when you're adding stuff across a double bond. You get the major product and you get the minor product. Yeah? There were certain situations in class where Markovnikov rule didn't apply and you did only get one product. That was because wherever you put something across the double bond, it didn't matter, you would get the same thing. That only happens when what? The only time you would add something across the double bond, but you get the same answer each time, is if it's starting with an S. Not saturated. Saturated means it's got the maximum number of hydrogens. Symmetrical. Good. If you have a symmetrical structure, whether or not you put it on one carbon in the double bond, whether or not you put it on the other carbon in the double bond, you get the same answer each time because it's symmetrical. Each half is a mirror image of the other. So if one product is possible for Z, that means that Z is the symmetrical one. And then it says two products are possible for Y. So two products possible for Y. It means that it's not each half of the structure isn't a mirror image of each other. So when you add stuff across the double bond, you do get two different answers. So two products are possible for Y. It's not a mirror image, it's asymmetrical. I always spell this one wrong. It's one S. Asymmetrical. Okay, we've already figured out X. X is structure 2, so you just have to compare 1 and 3. Uh, the symmetrical one is Z. Can you have a look at this? You already figured out 2, so you just have to look at 1 and 3. Out of 1 and 3, which one's symmetrical? 3 is the symmetrical one. Good. So 3 has to be Z, or I should say Z has to be 3. I've lost it. Z has to be 3, and therefore Y is structure 1. Okay, good. You've already figured out the three answers and you didn't even need to do any of the calculations. Okay, which would be nice. However, you don't just get marked on figuring out X, Y, and Z. You get marked on justifying your answer with reference to the information provided. Okay, it's a 7-mark question, which means even though we've already figured our answers, we do now have to confront the numbers. Okay? That's the point of the volume and concentration. We have to bring it in now. So now you could use the numbers to identify structures 1, 2, and 3 as X, Y, or Z, but we've already figured out X, Y, or Z based on the just the wording and the information alone. So we don't have to use the numbers to identify. We can use the numbers to confirm. Yeah? We can use the numbers to confirm that, what did we say? Structure 2 is X, structure 1 is Y, and structure 3 is Z. Okay, if the numbers match up, you should get these exact molar matches that molar masses, sorry, that uniquely identify the three structures. All right. So, what did we say? We said that X is, let's just start in order. We said that X is structure 2. All right. Now, what do you have here? Separate 0.1 gram samples of X, Y, and Z are titrated with 0.0617 molar sodium hydroxide. The tidal volumes are shown. Okay. If we say that X is structure 2, when we do the mole calculations for the sodium hydroxide, jump back to the X, we should get the matching what's it called? Matching molar mass for structure 2, which is 74.078. Okay, so let's see if that's true. Yeah. We're trying to identify something for X. We're trying to end up there, which means I should start my working out with the sodium hydroxide. Moles of sodium hydroxide. They've given you the concentration, 0.0617, and the volume that reacts with X is given in the table, 21.88. Okay, so concentration and volume, C times V, will give you the moles of NaOH. 0.0617 times 21.88 mils is 0.02188 liters. All right. If you pop this in the calculator, your answer for the moles of sodium hydroxide is 0.00135 mole. Okay. Now, normally when you're doing these calculation questions, if you're trying to relate different chemicals, you need the balanced chemical equation. Okay. With acids and bases, you don't need to go all the way to the equation though. You just need to know one thing about the acid. What is it? When we did module 6, sometimes you didn't get told the acid. You could figure out the general formula based on one thing they told you about that acid. Does anyone remember what it was? When we did practice questions in module 6, even if you don't know the specific acid, not weak or strong, not amphiprotic, close though. Something about protic. Yes, good. If it's monoprotic, diprotic, or triprotic, exactly. All you needed to know was how many OHs the base released and how many H's the acid released. Yeah, that's it. So X we said is structure 2. Have a look. Is structure 2 monoprotic, diprotic, or triprotic? Mono, because it's only got this acidic hydrogen here. So guys, the acid releases 1H plus, sodium hydroxide, NaOH releases 1OH minus. What's the ratio of the acid to the base then for this one? The acid releases 1H plus, the base releases 1OH minus. It's a 1-to-1 ratio. Good. So your moles of X should be your moles of NaOH, which is also the 0.00135 mole. All right. And then we said that we're using these calculations to confirm if the answer really is structure 2. And the way we confirm if that's the identity is if it matches the molar mass. So now that we've got the moles of X, we want the molar mass of X. So guys, your equation is moles is mass on molar mass, which means molar mass is mass on moles. Okay? They use the same mass each time. They kept using 0.1 grams. 0.100 grams divided by 0.00135 mole. Okay, so pop this in the calculator for me. What do you get for the molar mass of X? Does it match your answer for structure 2? If it's got one hydroxyl group, it's mono. If it's got two, it's di, and so on. If it's got one carboxyl group, yes, not hydroxyl, carboxyl. This. Yes, if you see two, then it's di. It does match. Yeah, so if you pop 0.1 divided by 0.00135 in your calculator, you get about 74.07 grams per mole, which matches the given molar mass for structure 2. Yeah. So this calculation confirms that X is structure 2. Okay. You can do the same things for the other ones. Why? We said, so is the reason why moles of X and moles of NaOH the same because of the molar ratio? Yes. If it's, you know how when you're doing the equation, if you had like, let's say you had HCl plus NaOH, turns into NaCl plus H2O. It's a 1-to-1 ratio, so you would tell me the moles are equal. Yeah. So likewise, X is monoprotic. HCl is also monoprotic, so this example is parallel to each other. So because the acid is monoprotic, the base only releases 1OH minus. When you go to balance it, it's 1-to-1. So likewise, the moles of the acid and base here are equal. Okay. We've confirmed X. We can do the same thing for Y. Y, we said earlier, is structure 1. So we want to work back to figure out the molar mass of Y and see if it matches the molar mass given for structure 1. So we do the same thing. Moles of NaOH is C times V. Concentration is the same, 0.0617. And then the volume that was used for Y is 22.99 mils or 0.02249 liters. When you pop your answer into the calculator for this one, your moles of NaOH is 0.0013876 mole. So again, we've got the moles of the base. We now need to relate it to the acid Y by checking if it's mono or di. Y we said was structure 1. So have a look at this one. Is structure 1 Y mono, di, tri? It's mono as well because it's got this one carboxyl group. The other hydrogens aren't acidic, so they won't pop off. Only this hydrogen will pop off. How do I know if it's mono, di, or tri? From module 7, the only organic acids you do is carboxylic acids with a carboxyl functional group. So the reason I know this is mono is because it's got one carboxyl functional group, C double bond to O with an OH. The other hydrogens are bonded to carbons. Those bonds aren't going to break off very easily. These hydrogens won't pop off. This is the only hydrogen that will pop off, so it's monoprotic. Yeah? Okay, so structure 1 is also mono, which means like the first one that I just did, it's a 1-to-1 ratio. So moles of Y is equal to moles of NaOH is equal to 0.0013876 mole. And then again, I want to confirm that Y is structure 1 by seeing if the molar mass matches. So I want to calculate the molar mass of Y and see if it matches structure 1. Mass on moles. Mass was used 0.10 grams. The moles this time is 0.0013876 mole. Okay, so pop this one into the calculator. What do you get for the molar mass of Y? And does it match what the question gives you for structure 1? The 0.10 grams, that was given to you in the question here. Separate 0.10 gram sample of X, Y, and Z titrated. It matches 1. So if you pop this in the calculator, you get, what did you guys say you get? We get 72.0665, 6667, 065-ish, which approximately matches your molar mass for 1. Matches structure 1. Good. So same thing, we do the last one for, we've done X, we've done Y, the last one we have to do is Z. And structure Z, we said, is supposed to be structure 3. So let's see if that's true. Calculate the moles of the base first, jump back to the acid after. Moles of NaOH, C times V. Concentration 0.0617 molar. And then guys, the volume for that reacted with Z is the same for as the volume that reacted with Y. So you should get the same moles. We don't have to pop this into the calculator twice. It should just give you the same 0.0013876 mole. And then now for me to jump to the moles of the acid Z, I have to figure out the molar ratio and see if it's 1-to-1 or 1-to-2 or whatever. Okay. This is structure 3. Mono, di, or tri? Di, because it's got 2 carboxyl functional groups, one on this side and one on this side. Okay. So if you've got, if you had a monoprotic acid, it was a 1-to-1 ratio. You needed the same amount of acid as the base. Yeah? This acid releases 2 protons. It's able to neutralize the base twice as fast. So listen carefully. Z is diprotic. It releases 2 protons. It neutralizes the base twice as fast. So if your moles of base is NaOH 0.0013876, when I go to moles of Z, am I timesing by 2 or am I dividing by 2? Your acid neutralizes the base twice as fast as the original monoprotic acid did. Are we going to divide by 2 or times by 2? To find out the moles of the acid. Let's figure it out by doing an example, yeah? So we're doing NaOH, and then just pick a random diprotic acid for me. Do you remember what was 6? Sulfuric. What's the formula for sulfuric acid? H2SO4, yeah. Okay, so I'm going to write up the formula for you. You guys balance it for me, yeah? Okay, how would you balance this? Two NaOH and one more. 2 waters. Good. Okay, so we're at the base at the moment. We just calculated the moles of the base. We're trying to go to the acid. You're going to times by 2, you're going to divide by 2. Oh, sorry, divide, yeah, times by 2 or divide by 2. To go to the acid, you're going to divide. Yeah. So it's a 2-to-1 ratio, which means you're going to divide by 2, which is the same thing as timesing by a half. That might have been what you were thinking about. You're dividing by 2, same thing as timesing by a half. Yeah. So the acid is twice as strong. You don't need as much of the acid anymore. So instead of timesing by 2, you're going to divide by 2. So moles of Z, because it's diprotic, is half times the moles of the NaOH it needs to titrate. Half times 0.0013876 mole. So when you do this, you actually only need about 0.0006938 mole of the Z. NaOH, monoprotic, diprotic is terminology we use for acids. NaOH, we just say releases 1 OH minus. Okay, so same thing. Now that you've got the moles of the acid, you're going to go molar mass is mass on moles, and let's see if it matches the answer for structure 3. Divide by 0.0006938. And what do you get for the molar mass of Z? 144.134 grams per mole, which, oh, you're getting different answers. 144.13-ish, which is approximately the one that's given. So this matches structure 3, like we said.